Okay. All right, balancing redox and basic solutions. You got notes already, right? And on the back, the first step is to balance it just like it's in acidic solution. So we're going to do exactly what we did on the quiz. And then we're basically going to correct for the fact that it's not in acidic solution, that it's in basic solution. What's running around in basic solutions?
Hydroxide.
Right. This time in basic solutions, we have hydroxides available and water. We don't have any H pluses. So we are going to balance it as if we have H pluses, but then we have to correct and get rid of those because we don't really have H pluses in that solution. Okay, so same steps. You're going to divide it into its two half reactions. And then we balance everything except for H and O. So over here, the C's and the N's are both balanced. Over there, the MN's are balanced. So now we have to balance the O's by adding water. So you're going to add 1 water to that side. Over here, you have 4 O's and 2 O's. So you're going to add 2 waters to this side. Then balance the H's by adding H plus. So you have 2 H's right there. So we need 2 H pluses right there. And we have 4 H's over here. So we need to add 4 H pluses. Not that you can read my writing, but 4 H pluses over here. Now you have to do the charges. This is the part you mess up. Do not mix up charges with oxidation numbers. Now we are looking at actual charges, so they have to be written in, right? Actual charges. All right, what's the charge on the left for this first half reaction? -1. What's the charge on the right for this first half reaction? +1. What's the charge on the left of the other one? +3, because that says 4H plus in case you can't read it. And then what's the charge on this side? 0. So how many electrons do we have to add on the first one and where? On the right side, and we need 2 of them. So we're going to add 2 electrons on the right. How many electrons are we going to add on the other half reaction? 3, and we're going to add them on the reactant side, right. So our common multiple for our electrons is 6, so we have to multiply that reaction by 2 and this reaction by 3 and then add them both back together. Can I do all that in one step? Okay. All right. This one? Well, it's going from +1 to -1. So you got to go to 0 and then to -1. So you need 2, right? All right, so I'm going to multiply and then add them all together all at the same time. So that's going to be 3H2O plus 3Cn minus. Then I'm going to go over here to this other one and do 6 electrons plus, 8 H pluses plus 2 MnO4 minus. And then all my products, I'll have 3 CnO minus plus 6 H plus 6 electrons plus, what's over here, 2 MnO2s plus 4 waters. Now I can consolidate anything that shows up on both sides, right? My electrons should always drop out. I have 6 H pluses that are going to go away, and that's going to leave me 2 on this side. I have all 3 of these waters are going to go away, and that's going to leave me 1 on that side, right? So my final balanced equation, as if it was an acidic solution, would look like this. Okay, did you get that?
Yes.
Yeah? Good. Okay, so we've got that down. All right, now to correct for the fact that it's in basic solution, what we're going to do is we're going to add hydroxides, and you're going to add the same number of hydroxides as H pluses that are left. So since I have 2 H pluses, I'm going to add 2 hydroxides. But when we add the hydroxides, we have to add them to both sides. Okay? What's going to happen when this H plus and this OH minus get next to each other?
Water.
They're going to make water. So those two are going to make 2 waters. So now I can consolidate the waters again, right? There's a water over here, and there's 2 over here now. Because that H plus that 2OH minus that you just added makes water. makes 2 waters. So I'm going to cross this water out, and I'm going to be left with 1 over here. Agree? So my final equation, if I can get it in on the bottom, will be 3Cn minus plus 1 water plus 2 MnO4 minus yields 3CnO minus plus 2 MnO2 plus 2 hydroxides. That's my final equation. Not that I can draw a straight line. Okay, so it's the same thing you've learned. It's just one more step. Right? We're just correcting at the end. Okay, try the next one. Try the next one in your notes. Huh? Oh, you need it? Okay, let me flip. Has everybody got what they need off this line? All right, there's the next one.
What are we deciding?
Balance that one in basic solution. And I'll do it, I'll write while y'all write.
Very confusing.
Think you got it? Almost. Sometimes it's easier to start over. Yes. Okay. Are y'all getting it in that little group right there? Because I didn't check. Okay. Okay. I think everybody's getting it.
I'm sort of afraid of getting it wrong. Just erase it all.
Oh, you're getting it right.
Okay.
You're getting it right. All right, that's what it should come down to. Well, you were getting it right. Oh, you are. You just haven't consolidated yet. You're right. Hey, I'll take it. Okay. Yeah, I need the tops. So when you finish something, I need the screw on tops. I need like 500 of them by Saturday. Yeah, but we did. I don't know. I didn't go to the cafeteria, but he supposedly made an announcement every day to do them. So I mean, surely in 2 days at lunch I'd have 500, right? I mean, there's 1,500 of you. The engineering is gonna volunteer at the Children's Museum Saturday, and they're making little catapults, and they're for the kids to put little mini marshmallows to shoot the marshmallows. So that's what they are. I'll wash them all. So yeah, don't worry about it. I'll
Does it
just go
depend on the bell? Does the ball cap depend?
Well, they can choose, and they can decide that. So anyway, all right, back to the lesson since we're recording. All right, we get it?
Yeah.
Okay, then let's move on to voltaic cells. Oops. What in the world? Let's try to do. Okay, here's what a galvanic or voltaic cell looks like. I have to make myself stay here and point. All right, so this I would put in my notes. Sometimes they're called galvanic cells. I tend to say galvanic cells. Your book uses voltaic cells. I think the AP test likes voltaic cells. Doesn't matter, same thing. Okay, looks like a mess, right? All right, what this really is just a single displacement reaction separated. Like it's not all taking place in one beaker. They've basically separated it and run a wire between them. What creates electricity? The flow of electrons. So if we can force electrons to flow through a wire, we have created electricity, right? So by separating this single displacement reaction, we have basically forced the electrons to run through the wire to go to the other one, right? Because what happens in redox reactions? Electrons are transferred. So we're just forcing them to go through the wire. Okay, that's kind of what this setup does. All right, so let's kind of look at this and look what's in here. We kind of have to dissect it and tell what it is. Is it big enough to see? Kind of. Might can make it a little bit bigger. It might get a little blurry with the words. Is that better? Okay. All right, so in this cell, because we say there's two cells, right? In this cell over here, there's an electrode. Both of these pieces of metal, right? You see that piece of metal and that piece of metal. Those are called electrodes. Okay? This electrode is made of what? Zinc. This electrode is made of copper. In the solution that's in the beaker, what ions are in solution? All right, so they put zinc nitrate in that solution of zinc nitrate in that half cell, in that beaker, yes? What happened to the zinc nitrate when it got put in water? It dissociated, right? Into its ions. So it dissolved and it dissociated. So the Zn2 plus is separate and the NO3s are there. All right, and then over here, what's in this solution? Copper nitrate. And they dissociated as well. All right, if you think about this reaction, which one of these, they wrote what's happening in one cell. There's what's happening to the cell on the left. Is that an oxidation or a reduction reaction? It's going from 0 to 2 and it's giving off electrons, right? So this one is the oxidation reaction. This one is the reduction reaction. If we were to put these two reactions together and do it all in one beaker, what would the overall reaction look like? Well, it doesn't matter that you put it in one beaker. What would the overall equation look like? Okay. So think about that reaction. Think about what's happening. What's happening to this electrode? As the zinc goes to zinc 2 plus, it had to give up electrons, yes? So those electrons are running through our wire. What's happening to the zinc atoms? What are they changing into? Ions. So zinc atoms that are in this electrode are giving up electrons. Their electrons are running up here through the wire, and then the zinc is going into solution. What's happening to the electrode over time? Yeah, it's corroding. It's getting smaller, right? Like pieces of this would be disappearing, right? The actual piece of metal would be getting smaller and smaller. All right, so the electrons run over here. Does this copper electrode need those electrons? No, those are copper atoms. They've got plenty of electrons, yes? So then where are the electrons going to run? Into the solution. When they hit the solution, who's going to want them? The copper 2 plus is going to want the electrons, right? So when it gets 2 electrons, what does it do? No, it goes from copper 2 plus to what? Copper solid. So what are you going to see happening over here? You're going to see some copper being made, either falling to the bottom or maybe even attaching to this electrode and this electrode getting bigger, right? So you're using up the zinc. The zinc is still there. It's going into solution, and the copper's being made. Okay, it's how you can zinc plate you can plate stuff, right? All right, so by running the electrons through the wire, we will get a voltage. Like if you put a voltmeter on here, you will get a voltage. All right, so that happens nicely. Then there's this thing right here. How many of you read the chapter? Oh, we got a few more. What is this thing called? The salt bridge. It has to be there. It has a function. Anybody know what the function is? Okay, it is. Let's look at it in a demo. Let's look at this. We're going to take what we have up here. Here's our little clock. Okay? And if I promise if I put a battery in it, it works. Maybe. Right? It works. Yes? Alright, so I'm pulling the battery out. And I'm going to set it up here. This container has these two leads touch, so it reacted. This solution has magnesium sulfate in it with a little bit of green food coloring, right? It should be clear. We got a little green food coloring in it by accident. This is copper sulfate. Copper sulfate is blue. And there's copper wire just wrapped around the spoon, just to get some more contact area. And this is magnesium ribbon wrapped around that spoon. And I've got alligator leads, okay? And I'm going to attach them to our clock. What?
That was making the noise for a second.
No, that's that clock behind me. If I can get them on there. Okay, is my clock working?
No.
What's missing?
Salt
Bridge.
The salt bridge. Here's our options for our salt bridge.
I like the sausage.
Which one do you like? The hot dog or the pickle?
Sausage.
Wiener.
The hot dog or pickle?
Wiener.
Why would you pick the pickle?
Hot dog?
Hot dog.
All right, we'll try the hot dog. If the hot dog, all right, so let me put them close enough together that it'll reach. If I put the salt bridge in, does anything happen?
You're not touching the
It's
blue
not
side. You're
touching,
not
it's
touching
not
the blue side.
No. Is it in?
Yeah, but it's not working.
What do you mean it's not working?
It's not working.
It's not moving.
Maybe because I left it sitting there. The clock's not moving?
No.
Maybe I have them backwards.
Maybe you should turn the hot dog.
No, I think the leaves are touching, and they may have exhausted some of our stuff. Because I think the leaves were touching.
Cucumbers in the bottom.
All right, so let's see if it works. It doesn't like me. I'm pretty sure. All right, try the pickle. Not effective if it doesn't work.
What a demo.
What a demo. Sorry. Worked last block just fine.
Yeah.
One time use.
Yeah, one time use. I really do think my leaves are touching. Pickle work?
No.
Yes! Oh, I broke my pickle. Is it still working? Okay. So maybe my hot dog got rid of all its salt. All right, so obviously to work, my pickle's in half. All right, so in order to work, you must have that salt bridge there, right? Because it's not working now, right?
Yeah.
I need Ina for checkout, please.
Okay.
Thank you.
That's impressive. Here, you want me to try a new hot dog?
How many hot dogs do you have?
I brought 3.
Ooh, can I have one?
Does that hot dog work?
Yes.
Okay, so maybe my hot dog would. No, it doesn't work?
No, it works.
Don't tell me no, I can't see it. Okay, so that hot dog works. All right, so hot dogs work. Just that one had done whatever. All right, so obviously the salt bridge is important. What does the salt bridge do?
It allows
All right, and that is probably the most common mistake. It does not. It does not complete the circuit. Okay, and that is what everybody thinks. They think the electrons run across the wire, then they go in here, and then they run back, and then they go like a circuit. That is not what happens, because those electrons are being gobbled up by that Cu2+, right? So what is the function of the salt bridge? It doesn't work if we don't have it. It balances the charge in the solution. Think about the zinc side. The zinc is losing the electrons, and every time it does, you keep adding a zinc 2+ to this solution, right? Well, those nitrates, there's only so many of them when you put the zinc nitrate in, right? So as you add more and more positive charges, the charge becomes unbalanced. It's not neutral anymore, right? And over here, what's happening to the charge over here? It's becoming more and more negative because you have less and less copper 2 pluses in solution, right? So it's not that you're really adding more nitrates, it's just that you have more per copper that's in there, right? So once this builds up a negative charge over here, in fact, once one copper goes to a copper atom, are the electrons going to want to run over here anymore? No, because they're not attracted to the negative charge solution, right? So they won't move. So the function of the salt bridge is to balance the neutrality or make the solution neutral again. So the nitrates, this particular salt bridge is made up of NaNO3. It doesn't matter what salt, right? It just needs to be a soluble salt. So the anions are going to run to this side to balance out all those extra Zn2 pluses. The cations are going to run to this side to balance out the NO3 minuses that are going to be left in solution when all the copper's gone, right? That is the function of the salt bridge. It's to balance the charge in solution, not run electrons back and forth. Okay? All right, so some other vocabulary that we need to know. Anode and cathode. The anode is where oxidation takes place, and the cathode is where reduction takes place. Most of the time they write cells where the anode's on the left and the cathode's on the right. It does not have to be that way, and the AP test inevitably will flip them just to make sure you know what you're doing. So the electrons will always run from the anode to the cathode, so you can think alphabetically. They will always run from the anode to the cathode. And the way you can remember the oxidation is at the anode, anox and red cat. So oxidation happens at the anode, reduction happens at the cathode. Anox and red cat. Deja vu?
No, like legitimately clear.
Well, in the book is like they're both vowels and both consonants.
Okay, both vowels, both consonants. That's how they had you remember it. And those are both, okay, whatever. Find a way to remember it. Okay? All right, so
Did you say that the anode always runs to the cathode?
the electrons will always run from the anode to the cathode. So if electrons are negatively charged and they run to the cathode, then the electrode on the cathode side is what charge? Positive. And what charge on the anode side? Negative. They are the source of the electrons, and the electrons run to the positive side. Okay? All right, let me give you a little worksheet. And let's see, we should be able to answer all but 2 questions on it. And those 2 questions we'll come back to in a minute. All right, here's just licked my finger and it had pickle juice on it. And hot dog juice, I think that's for it. I'm not. Yeah, let's hope that copper sulfate. We're not staying here long, so don't get real excited. I'm gonna be on board in a minute. I think that's 3. I always miss count, see? I can't get on board. All right, so look at the voltaic cell that's on your picture. All right, and we're gonna, I'm gonna give you a little hint on the first one, and then we'll answer the rest of them, and I'll kind of come back to that in a second. But that's what we're getting there. Hang on. All right, I'm just gonna draw. Don't laugh at my drawings. I'm just gonna draw a quick sketch. No laughing. Looks like a car.
Looks like the little beetle bug that you tried to draw.
Oh, all right, there's my little salt bridge that doesn't fit in my water. All right, so this side has aluminum nitrate, and this is a piece of aluminum, and this is lead, and this is lead nitrate. Okay, so the first question asked you, what is more easily oxidized, the aluminum or the lead? The only way you have to know that at this moment is your activity series. Does anybody remember which one is more reactive, the aluminum or the lead? Which one? The aluminum is. So the aluminum is more easily oxidized. And I'll show you another way to find that out in just a minute, but let's kind of make sure we understand this picture.
And then the bucket so that lithium was like that.
Right. Yeah, because we're not there yet. All right, so what is the balanced equation showing the spontaneous reaction that occurs? All right, so if aluminum is more reactive and it's spontaneous, then aluminum has to be what's oxidized. So aluminum's going to go from aluminum to aluminum 3+, right? What does lead then have to do? Well, it has to, right, it has to gain the electrons, right?
Oh yeah.
So it's going to go from lead 2+ to lead. All right, now it says balance it. You can balance it like your redox, but this one you can probably balance by inspection. It has to balance for charge and atoms. So we're going to have to put a 3 there and a 2 there for the charges, right? Which will force you to put a 2 there and a 3 there. All right, and then the next question we can't answer yet because I haven't shown you the voltages. It says, what is the maximum voltage that the cell can produce? Hold that thought, and let's keep going. All right, number 4, what is the direction of the electron flow in the wire? That means we have to figure out what's being oxidized. What's being oxidized is losing the electrons, right? Because Leo goes grr. So losing electrons is oxidation. So which side is losing the electrons? The aluminum is losing the electrons. So the electrons are running from left to right.
Left to right.
Sure, or from aluminum to lead. All right. Then what is the direction of the positive ion flow in the salt bridge?
Right. This way. It's going to the lead.
All right, here's your salt bridge. So let's just say it's NaNO3 again. Which one's going to want to run? What's building up on this side?
Negative.
Negatives are building up on this side, right? Because your leads are going into the lead atoms. So the positive ion is the cation, so it will run this way because the negative charges are what's building up in here. Okay, so it will be to the lead. All right, number 6, which electrode is decreasing in size? The aluminum. The aluminum is decreasing in size because it's giving up the electrons and you're getting more and more Al3 pluses in solution. Which electrode is increasing in size? The lead. The lead's going to start building up on that electrode. All right, what's happening to the concentration of aluminum ions? It's increasing, right? As it loses electrons, you make more and more Al3 pluses. What's happening to the concentration of the lead ions? They're decreasing because your lead 2 pluses are going away and becoming lead atoms. All right, we can't, okay, what is the voltage in this cell when it reaches equilibrium? That's 0. Although you don't know what that is yet. All right, number 11, which is the anode then? The aluminum is the anode. It is what is oxidized. It's what's losing the electron, so it's the anode. So then the lead has to be the cathode. What is the positive electrode? The lead. The lead. Remember, the electrons are going to run to the positive electrode, right? So they're going to run towards the lead. And then which one's the negative electrode? The aluminum. Okay, so do we understand the picture of a galvanic cell? All right, so now we have to figure out how to get this voltage, right? This voltage up here. How do we get that? We can measure it with a voltmeter if we're in the lab, but if we're not in the lab, we've got to have a way to do it. And to do it, there's nice tables we can use. But where did those tables come from? They came from setting up this kind of apparatus. Basically, they set a standard, and the standard is hydrogen. So this side of this particular cell is a standard hydrogen electrode. Yeah. Is hydrogen a metal?
No.
No. So hydrogen can't be an electrode, right? It can't be the piece of metal that sticks down in there because it's a gas. So what metal did they use? They used platinum. Why did they use platinum?
That's cool.
It's not
Expensive.
very reactive. Right. It's a non-reactive or unreactive metal. So they can use it. We still need the piece of metal because we need the electrons to move, right? We need something that will conduct electrons. So we need something. We just don't want it to react with what's in solution. So we need a non-reactive metal because this is an acidic solution down here, right? There's H pluses running around. So we need something that's not going to react with that. So platinum is the choice. So there's a platinum wire there. They have bubbled in. There's hydrogen gas going in and bubbling it into solution. 1 bar is the same thing as 1 atmosphere. That's the pressure of it. But anyway, they bubbled in the hydrogen. They have a solution that has some H pluses running around in it. And then, so this is one side of the cell. On the other side, they just put some metal, any metal, and measured the voltage. Okay, so they put every metal against hydrogen and measured the voltage, and then put it in a table. Okay, and there's tables that are much more extensive than that. That doesn't even have everything we need on it, right? So you can Google reduction potential tables. That's usually what you can look up, reduction potential tables. It is also in table 20.1 in your book, but either way is fine. All right, so notice these, what do they have for hydrogen? 0, because they picked hydrogen as the standard to compare everything else to, right? So if they put hydrogen on the other side, nothing's going to happen, so it's 0. So that's the standard. All right, so then we don't really care. They could have picked anything to be the standard because when we go to calculate the voltage, voltage is the difference. So all we care is how far apart they are, okay? So we're going to calculate the cell voltage, but now there's lots of words for this. You can say cell voltage. You can say cell potential. You can say potential difference. You can say electromotive force. I don't know if I spelled that right. All of those mean the same thing. And they're represented by capital E with a 0 little degree sign at the top. And then usually we indicate what that voltage is for. So if we're doing it for the whole cell, we usually call it E of the cell. And that's how we write it. That little degree sign at the top indicates that you're at standard conditions. All right, do not mix up standard conditions with STP. It is not the same thing. Okay, don't mix them up. Standard conditions are at room temperature, so that's 25 degrees C. If it's a gas and has a pressure, it has to be at 1 atm, and if it's a solution, it has to be at 1 molar. Those are standard conditions. Okay, unlike STP, which is 0 degrees C, by the way. All right, so standard conditions, that's what that degree sign means. All right, we can calculate that, and the way your book calculates it, they say E of the cell is equal to the cathode's reduction potential minus E of the anode's reduction potential. I do hear it. Okay, so the one, I don't think we have the one on our thing. Anybody got their computer up? Nobody has their computer up. Okay. The one you just did on your sheet had aluminum and lead, right? All right, we have aluminum, but of course the one that I pulled and picked on here does not have lead, and I didn't check ahead of time. So we're going to Google another one. And let's see if we can find one that has a little more. Oh. I didn't mean for all that. I just wanted the picture. All right, does this one have lead? Where's lead? You see it? No, not that one. The one that just has lead. I don't see it on that one either. Of course, not the one I pulled up. I really don't. That looks like it's more metals. There are other things that oxidize besides the metals. That's the. We see lead on that one? There it is. There it is, right? All right, so lead is negative 0.13. Can we remember that? All right, so I'll write it in for us on this one. All right, negative lead plus 2 electrons to Pb was negative 0.13. All right, so what was our anode in that case? Aluminum. And then our cathode was lead. And so our equation is cathode minus anode, right? So our E of the cell, which will go back and answer number 3 on that worksheet, E of the cell is going to be the negative 0.13 volts from the lead minus a minus, what was the number? 1.66. Which comes out to be some positive number. Somebody, is that right? All right. It must come out positive. In order for it to actually be a galvanic or a voltaic cell, it has to be a spontaneous reaction. And to be spontaneous, that E of the cell, the voltage, has to be positive. So if it doesn't come out positive, something's wrong. Okay? All right, now I tend to not do that. I don't tend to do cathode minus anode. I basically look at it and then kind of figure it out and force it. And then I add. What I do is, all of these are written as reductions, right? So if I had silver, which is up here, and I was reacting it with iron, right? And I wanted to know which one was the anode or which one was going to be oxidized, which one was going to be reduced. I have to have these two things add up to a positive number. But I have to reverse one of the reactions. Why do I have to reverse one of the reactions? Yeah, how are they all written on that table? As reductions. If I have a reduction, I have to have a what? An oxidation. So I have to flip one of them. When I flip the reaction, you change the sign of the potential, of the voltage. So which one of these would I have to flip to still get them to add up to a positive number? Iron. So I think of it this way, and I flip, and you can do it any way you want, but I flip, and then I change the sign, and then I always add. So my cell voltage would be, what's 8 and 4? 12? 1.24? So my cell voltage for that made up cell would be 1. Do you see that? Which one would be the anode? The iron, the one I flipped, right? The oxidation, the one that you had to reverse to be oxidation would be the anode. The other one would be the cathode. Okay, are we starting to see it a little bit? Okay, another way to describe, which one, so the first question said which one's more easily oxidized? Oxidized would mean which one would be more likely to reverse off this table, right? Which ones would we be more likely to reverse? The bottom ones, the negative ones. So lithium is the most easily what?
Oxidized.
It's the most easily oxidized. So it is the most reactive metal. So now you no longer need an activity series, right? Because if you have this, you've got both, right? Makes sense? These up here are the most easily reduced, which makes sense. They're reduction tables and they're positive, right? So they're more easily reduced. Okay. So that will let you tell which one's doing what. There's something else I was getting ready to tell you. Oh, another way to summarize a cell. There's a shorthand notation. Let's say we were doing the one that y'all did on your worksheet. So it has the aluminum nitrate over here and has the lead nitrate over here, right? And then it has the electrodes and it's connected in your solver. Okay, so there's your little picture. Instead of drawing that picture, you can write this. You can put all the ions. Sometimes they drop those nitrates. And they just do it like this and just put the metals and they don't put these. All right, so what does this shorthand notation mean? This side, the left, in this case, the left is always the anode. The double line, right? This double line in the middle separates the two half cells and the other side's the cathode. These other straight lines indicate a phase change, a difference between the phase. This is aluminum solid. This is a metal. This is aqueous. This is aqueous. This is solid. So these single lines indicate a phase barrier, basically. And then the double lines in the middle indicate it's where the cells separated. Okay? How would we write it in that notation for this cell? Let's assume this is a metal. Yeah, this one's reduced. Okay, so this one's the anode, right? Because look at the picture, right? This is decreasing. So this is the anode, this is the cathode. How would I write that shorthand notation for this cell? M, whatever the metal is, then a line, then what? M plus, and then two lines. H plus, H2 gas, and guess what? They'll do another line for the platinum metal because it's another phase. It's another phase, right? And it's in there, but they will. Huh? It doesn't really do anything. I do think they'll put it in there. A lot of times you have them where it's two ions that change oxidation numbers, and you have platinum metal. So you might have two ions in there. Anyway, just shorthand notation in case you see it on you will see it on your homework on the Mastering Chem. All right, questions? That's it. Think we got it? Was it too bad?
Not really.
Okay. All right, you have homework. You have a Mastering Chem assignment that goes through all these voltaic cells, and guess what you have next time? You have a quiz on the galvanic voltaic cells.
Are quiz basis
It'll be similar to the worksheet or the Mastering Chem. They kind of do the same thing.
is the base oxidation reaction?
That could be. You could have to balance in basic too. Everything I taught today is fair game for a quiz.